Welcome to another deep dive. Today, we're going to be looking at, we're going to be diving into advanced mathematics.
Right.
Specifically exceptional sets.
Okay.
And we're going to be looking at these in the context of orthogonal projections.
Cool.
And the paper that we are going to be using to guide our deep dive today is Bounding the Dimension of Exceptional Sets for Orthogonal Projections.
Wow, what a title.
Yeah.
It's a mouthful.
It is. And it is by Cholak, Cerniai, Lutz.
Two Lutz.
Two Lutz.
Yeah. Okay.
Mayordomo and Still.
Wow. That's quite the author list.
It is quite the author list. So before we jump in,
okay.
I just want to make sure that we're all on the same page with what orthogonal projections were.
Okay, yeah, let's do that.
All right, so you can think about orthogonal projections like shining a light on an object and looking at its shadow.
That's a good way to think about it. I like that.
Right. So you have like a 3D object and you shine a light on it, it's going to cast a 2D shadow.
Right, exactly.
And so that shadow is like the orthogonal projection of that 3D object onto a 2D plane.
Yeah, and we're going to be thinking about how the dimensions of sets change under these projections.
Right.
So how that shadow's size relates to the original object's size.
Right.
But we're not going to be using our usual way of measuring size, like with lengths or areas or volumes.
Right. We're going to be using Hausdorff dimension.
Exactly. Hausdorff dimension lets us measure the size of sets that go beyond our usual 1, 2, 3 dimensions.
Yeah, it's a way to capture the complexity of sets that are maybe a little more intricate than just like a line or a square or a cube.
Yeah, think of the Cantor set, for example.
Right, the Cantor set.
You keep removing the middle third of a line segment over and over again, and you end up with this set that has 0 length, but it still has some size to it.
Right.
It's got this intricate structure, and Hausdorff dimension lets us measure that.
Yeah, so Hausdorff dimension gives us like a more nuanced way to talk about the size of these unusual sets.
Yeah.
And the central question that this paper is looking at is, what happens to this dimension when we project a set onto a lower dimensional space?
Exactly. We know from Marstrand's theorem that in most cases, the dimension of a projected set behaves as we expect.
Right. It kind of makes sense.
Yeah, but there are these weird cases where the dimension drops a lot more than we'd expect.
These are our exceptional sets.
Yeah, and those are what make this whole thing so interesting.
So interesting.
This paper is all about figuring out just how big these sets of exceptions can actually be.
Right, and they introduce this notation to help quantify that. T of NKANS.
Okay, and this represents...
So that's TNKAS.
Yeah.
Okay.
And that represents the maximum possible Hausdorff dimension of an exceptional set when projecting from an n-dimensional space to a k-dimensional subspace.
Right.
So we're going from like a higher dimension to a lower dimension.
Exactly.
The original set that we're projecting has dimension A.
Okay.
And the projected set ends up with a dimension that's less than as. Okay, so it's kind of capturing the worst case scenario, right?
Exactly. It's like, what's the biggest possible size of this exceptional set that we can get?
Yeah, and people have been trying to figure this out for a while.
Right. There's been tons of research on this T function.
Kaufman, Mattila.
Falconer.
Paris, Schlag, Rudin.
So many people have worked on this.
It's a hot topic.
It's a hot topic.
And this paper builds on all that work.
Yes.
They introduce this new function.
SNKAS.
Yeah.
And they prove that it's a lower bound for TNKAS.
Okay, so that means you can't have an exceptional set bigger than this S function.
Right.
No matter what.
No matter what.
That's pretty cool.
It is pretty cool. And what's even cooler is that in certain cases, this S function isn't just a lower bound.
Oh.
It's also an upper bound.
Really? So they figured out the exact size of these exceptional sets.
Wow.
In which cases?
Specifically when we're projecting onto lines, so K1.
Okay.
Or when we're projecting onto hyperplanes, so KN1.
Wow. So they've nailed it down for those cases.
Yeah, they've cracked the code.
That's exciting.
It's super exciting. I'm really excited to see how they did this.
Me too. Let's dive into the proof.
Let's dive in.
Welcome back to our deep dive into exceptional sets.
It's been a wild ride so far.
Yeah, we've really gone deep, haven't we?
We have.
Okay, so we left off talking about how the authors proved that their S function is not just a lower bound for TNKAS, but also an upper bound.
Right. At least for those special cases of projecting onto lines and hyperplanes.
Exactly. And they do this with a really clever proof technique.
Okay, I'm all ears.
So remember those NKAAC pairs we talked about?
Yeah, those are kind of a mouthful.
They are, but they're really useful for this proof.
Okay.
So the authors use these pairs along with 4 key lemmas and an inductive argument to establish their upper bound.
Okay. Lots of moving parts here.
There are, but it all fits together beautifully.
Okay, I'm ready to see how it works.
So let's start by looking at lemma 2.1. This is where they start tackling the case of projecting onto lines. So KA1.
Okay, lines first, then hyperplanes. Makes sense.
So this lemma says that if you have an n plus 1, 1 AST pair, and those parameters meet certain conditions.
Like what kind of conditions?
Well, specific values for A, S, and T that ensure things work out nicely in the proof.
Okay, so if you have this specific kind of pair.
Right, then you can construct an N1 AST1 pair from it.
So we've gone from n plus 1 dimensions to n dimensions.
Right, exactly. We've stepped down one dimension.
And t is smaller than t, right?
Yeah, it's just a tiny bit smaller.
Okay, so they're linking an exceptional set in a higher dimension to a slightly smaller one in a lower dimension.
Exactly, and they use Marstrand's projection theorem to do this.
Ah, the good old shadow theorem.
Yeah, exactly. They basically show that if the exceptional set in n plus 1 dimensions were too large.
Too large meaning?
Meaning its dimension t were too big.
Okay.
Then its projection onto n dimensions would violate Marstrand's theorem.
Like the shadow would be too big for the object.
Right, so it just wouldn't make sense.
So they're using Marstrand's theorem to rule out exceptional sets that are too big.
Exactly. It's like a constraint on the size of these sets.
That's really clever.
It is, and it sets up their inductive argument nicely.
Okay, so that's lemma 2.1. What about lemma 2.2?
Lemma 2.2 is also about projecting onto lines still K1.
Okay.
But this time they show that under certain conditions, you can construct an N1A1ST pair from an N plus 1 AST pair.
So now they're not just shrinking the exceptional set, but also the original set.
Right, they're reducing A by 1.
Why do they need to do that?
It's all part of their plan to build this chain of inequalities that leads to their upper bound.
Okay, like a domino effect.
Yeah, exactly. By tweaking both the dimension of the exceptional set and the original set, they're setting up the pieces for their induction.
Okay, I'm starting to see the big picture here.
And to prove this lemma, they use a combination of Marstrand's projection theorem and a clever slicing technique.
Slicing, like cutting a cake.
Haha, kind of. They're carefully slicing the original set in n plus 1 dimensions to create cross-sections that have the properties they need.
Okay, so they're using both projection and slicing to manipulate the set and connect those different dimensions.
Exactly. It's all about finding those hidden relationships between the dimensions.
This is getting pretty abstract.
It is, but that's the beauty of math, isn't it?
Uh-huh, I guess so.
Okay, so we've seen how they handle projecting onto lines. What about hyperplanes?
That's the K in one case, right?
Right.
Bring on the hyperplanes.
Right. So for this, they have lemma 2.3 and lemma 2.4.
Okay, 2 lemmas for hyperplanes.
Yeah.
Makes sense. They're trickier.
They are more complex.
So what does lemma 2.3 say?
It's actually pretty similar to lemma 2.1.
Oh, really?
Yeah, they show that if you have an n plus 1 NAST pair with certain conditions on a NS,
Okay.
then you can construct an N1 AST pair where T is a bit smaller than T.
So they're stepping down a dimension again, shrinking the exceptional set as they go.
Exact. The same strategy, different projection.
And they still use Marstrand's theorem for this.
They do, but they have to adapt it to work with hyperplane projections.
Okay, because hyperplanes are different beasts altogether.
They are. Remember, a hyperplane is like a flat slice through a higher dimensional space.
Right, like a plane in 3D space.
Exactly.
Okay, so Marstrand's theorem still applies, but with a twist.
Right. It tells us that the dimension of the projected set is usually preserved as long as the original dimension isn't too large.
Okay, so it's all about making sure the target space is big enough to accommodate the projection.
Right. And those conditions on an S in the lemma make sure that everything works out nicely.
Okay, so they've carefully set the stage for Marstrand's theorem to do its magic.
Exactly. And that leads them to the connection between exceptional sets in n plus 1 and n dimensions for hyperplane projections.
Okay, that's lemma 2.3, one more to go.
Right. Lemma 2.4 is the grand finale for hyperplanes.
Okay, what's so special about this one?
This is where they prove that under specific conditions, you can construct an N, N1, A1, S1, T1 pair from an N plus 1 NAST pair.
Whoa, that's a lot of changes happening at once.
I know it's the most complex of the 4 lemmas.
Okay, so they're shrinking the exceptional set, reducing the dimension of the original set, and also shrinking the target space.
You got it. It's like a triple whammy.
Wow, they're really pulling out all the stops here.
They are. And to do this, they combine Marstrand's projection theorem with Mattila's slicing theorem.
Okay, 2 powerful theorems working together.
Yeah, it's a beautiful combination.
So tell me how they use these theorems, I'm curious.
Well, they carefully choose a hyperplane in n plus 1 dimensions and project the original set onto it.
Okay, so that's the Marstrand part.
Right. Then they use Mattila's slicing theorem to pick out specific cross-sections of this projected set.
Okay, so slicing comes after projecting.
Exactly. And they choose these cross-sections very carefully to make sure the dimensions of the resulting sets match up with the parameters in their N1, A1, S1, T1 pair.
Wow, it's like they're tailoring the sets to fit their needs.
Exactly. They're masters of mathematical tailoring.
Okay, so they've got these four lemmas, each connecting exceptional sets in different dimensions for both line and hyperplane projections.
Right. All the pieces are in place for their inductive argument now.
Okay, I'm ready to see how they put it all together.
But I think we should take a break here.
Yeah, good idea. My brain is starting to melt a little.
We'll pick up the induction part in the next segment.
Sounds good.
Yeah.
I'm eager to see how they nail down that upper bound.
Okay, so we've made it to the final part of our deep dive into exceptional sets, and I'm ready to see how this induction thing actually works.
Yeah, the moment of truth.
So remind me again, what's the big picture here? What are we trying to prove with this induction?
Right, so we're trying to prove that their S function that they came up with is not just a lower bound for the size of these exceptional sets.
Right, we already talked about that.
Yeah.
But it's also an upper bound, at least for those special cases when we're projecting onto lines or hyperplanes.
Okay, so we want to show that the exceptional sets can't be bigger than S, and they also can't be smaller than S.
Exactly, at least not in those specific cases.
Okay, so how does induction help us do that?
Well, with induction, we start with a base case, something we already know to be true.
Right, like a solid foundation.
Exactly. And in this case, our base case is the scenario in 2 dimensions.
Okay, 2 dimensions. Why 2 dimensions?
Because for 2 dimensions, we already have really precise results thanks to previous work by Kaufman and others.
Oh, right. I remember you mentioning Kaufman earlier.
Yeah, so for N2 and K11, or
Yeah.
K-array1, meaning we're projecting onto lines or hyperplanes in 2 dimensions.
Okay.
We already know that our S function gives us both a lower and upper bound for the size of the exceptional sets.
Okay, so the complete statement we're trying to prove is already true in 2 dimensions.
Exactly. So that's our solid ground, our starting point.
Okay, so we've got our base case, but what about all the other dimensions? How do we get from 2 dimensions to 3 dimensions to 4 dimensions and so on?
That's where the inductive step comes in.
The magic step.
Right. So the inductive step says that if our statement is true in n dimensions,
Meaning the upper bound holds in n dimensions?
right, then it must also be true in n+1 dimensions.
Okay, so if we can prove that, then we're golden.
Exactly, because then the truth of the statement in 2 dimensions would imply its truth in 3 dimensions.
And the truth in 3 dimensions would imply its truth in 4 dimensions and so on.
Exactly, a domino effect of truth.
Okay, I like it. But how do we actually prove this inductive step? This is where those 4 lemmas come in, right?
You got it. Those lemmas are the key. They provide the bridge between dimensions.
Okay, I'm starting to see how the pieces fit together.
So remember lemma 2.1 and 2.2? Those were about projecting onto lines.
Right, shrinking the exceptional set, and maybe shrinking the original set as well.
Exactly. And then lemma 2.3 and 2.4, those were for hyperplanes.
Also shrinking things, but in a more complex way.
Right. So each of these lemmas provides a specific way to connect exceptional sets in n+1 dimensions to exceptional sets in n dimensions.
Okay, so they're like our tools for moving between dimensions.
Exactly. And here's how we use them in the inductive step.
Okay, lay it on me.
We start by assuming that our upper bound is true in n dimensions.
So we're saying let's pretend it's true for now.
Kind of, yeah. It's called the inductive hypothesis.
Okay, so we assume it's true in n dimensions, and then what?
Then we consider a potential exceptional set in n+1 dimensions.
So we're like, okay, let's imagine there's an exceptional set in n+1 dimensions that's bigger than our S function.
Right. That would break our upper bound.
Right, so we want to show that this can't happen.
Exactly. So what we do is we carefully analyze different cases based on the values of K, A, and S.
Okay, so we break it down into smaller pieces.
Right. And for each case, we apply one of our 4 lemmas.
So we pick the right tool for the job.
Exactly. And that lemma connects our exceptional set in n+1 dimensions to a corresponding exceptional set in n dimensions.
Okay, so we've gone down a dimension.
Right. And since we assumed that our upper bound is true in n dimensions,
At our inductive hypothesis.
right, we know that the exceptional set in n dimensions can't be bigger than our S function.
Okay, that makes sense.
And because our lemma links the exceptional set in n+1 dimensions to the one in n dimensions,
We can use that information to constrain the size of the exceptional set in n+1 dimensions.
exactly. We create a chain of inequalities that ultimately shows that the exceptional set in n+1 dimensions also can't be bigger than our S function.
Wow, so like a domino effect. The truth in n dimensions forces the truth in n+1 dimensions.
Precisely. It's a beautiful chain reaction of logic.
So they do this for all the different cases, all the different combinations of K, A, and S.
Yes. They meticulously work through each scenario, making sure that no matter what, the exceptional set in n+1 dimensions is always bounded by our S function.
Okay, so that completes the inductive step.
It does, and since we already know that the base case is true, the dominoes start falling.
The upper bound holds in 2 dimensions, which means it holds in 3 dimensions, which means it holds in 4 dimensions, and so on.
Exactly. We've proven it for all dimensions for those special cases of projecting onto lines or hyperplanes.
This is incredible. They've really solved this problem.
They have. It's a major accomplishment.
And it all comes down to those 4 clever lemmas and this elegant induction argument.
It's a beautiful example of mathematical ingenuity.
Well, I have to say this has been a truly mind-bending deep dive.
Yeah, we've really gone deep into the world of exceptional sets.
But it's been so rewarding to see how these mathematicians tackled this challenging problem.
Absolutely. It's a reminder of the power of human curiosity and the beauty of mathematical reasoning.
And I think the biggest takeaway for me is that there's still so much more to explore.
Oh, definitely. This paper has opened up new avenues of research, new questions to ask, new puzzles to solve.
It's like they've shown a light on a whole new mathematical landscape.
And it's waiting for us to explore it.
Exactly. So to all our listeners out there, keep exploring, keep questioning, and keep diving deep into the fascinating world of mathematics.
Until next time.
Welcome back to the deep dive. We're going to be looking at exceptional sets in orthogonal projections. And I have to say, even just glancing at this paper by Cholak, Cernyai, Lutz, Mayordomo, and Stuhl, it's pretty dense. But thankfully, we have an expert here to walk us through it, ready to tackle this.
Absolutely. It is a dense paper, but the results are really elegant. We're basically looking at how much the dimension of a set can shrink when you project it onto a lower dimensional space. So imagine shining a flashlight on a 3D object and observing its shadow.
Okay.
Most of the time, the shadow will be 2D, but at certain angles, it could collapse into a 1D line. And that's kind of what we're investigating here, those exceptional projections.
Okay, that's a good analogy.
Yeah.
So I'm guessing these exceptional sets aren't just some mathematical curiosity. They probably have implications for other areas of math and maybe even physics.
Yeah, for sure. They show up in a lot of different areas. Like in geometric measure theory, they help us to understand the structure of fractals and other complex geometric objects. And in harmonic analysis, they come up when studying Fourier transforms. So yeah, they have implications beyond just abstract geometry.
That's really interesting. So to get started, let's make sure we're all on the same page with the terminology. The paper mentions things like analytic sets and Hausdorff dimensions and the Grassmannian. Can we clarify those for our listeners?
Sure. Let's start with analytic sets. Just think of them as like a general category that includes most geometric shapes that you can think of. Curves, surfaces, solids, even fractals. They basically have nice geometric properties.
Okay, so that's our playing field, the sets we're working with. What about Hausdorff dimension? I know it's a way to measure size, but it's not the typical length, area, volume.
Yeah, that's right. Hausdorff dimension goes beyond those simple measurements, and it captures how rough or fractal a set is. It can even assign a non-integer dimension to a set, which is useful for describing fractals that have dimensions between whole numbers.
Right, like the Mandelbrot set with its fractal coastline. Okay, so Hausdorff dimension helps us to measure those complex structures. Now, what about the Grassmannian?
The Grassmannian, it sounds complicated, but it's just the set of all k-dimensional subspaces within an n-dimensional space. So like if you're in 3D space, the Grassmannian includes all the lines, planes, and of course the whole 3D space itself. It helps us to study all the ways you can slice through higher dimensional space.
Okay, that makes more sense. So we have these analytic sets, which we're measuring with Hausdorff dimension, and we're projecting them onto subspaces from the Grassmannian. Now, where do these exceptional sets come into play?
Well, there's a classic result called Marstrand's projection theorem from the 1950s. It basically says if you project an analytic set in 2D onto a line, for almost every direction, the Hausdorff dimension of the projection is what you'd expect. It's the minimum of the set's dimension and the dimension of the line, which is 1.
That makes sense. But you said almost every, which means there must be exceptions, right? And those are our exceptional sets.
Exactly. Marstrand's theorem says those exceptional directions are rare, but then the question is, like, how rare are they? How big can those sets of exceptional directions be? And that's where the idea of bounds on their Hausdorff dimension comes in.
And Mattila extended Marstrand's theorem to higher dimensions, right?
Yes. Mattila showed that it's not just limited to 2D, it works in higher dimensions too. But again, we still have these exceptional sets, and we want to understand how big they can get in those more complex scenarios.
So this paper that we're looking at is tackling this problem. They're trying to define the bounds of the dimension of these exceptional sets more precisely.
Exactly. They introduced a new function denoted subn, CEAAAS, which provides a lower bound on the Hausdorff dimension of the exceptional set. It's basically saying the exceptional sets can't be smaller than this.
Okay, so that's their big contribution, this sub-cos of function. And they use it to prove the exact bounds for two specific cases, right? When K1 and Kn's 1.
Yeah. And they show that their lower bound, given by Sapan-Kesub, is actually the best possible bound. There are exceptional sets that actually have that exact dimension.
Wow, so they're not just saying here's a bound, they're saying here's the best bound. And they do this by actually constructing exceptional sets that reach that limit.
That's right. They don't just prove it theoretically, they actually show you how to build sets that achieve those bounds.
That's amazing. Okay, I want to make sure I understand this sub-KK sub-function a bit better. Can we unpack it a little?
Of course. It's defined in definition 1.2 of the paper, and it's a piecewise function. So it takes on different forms depending on the values of n, k, a, and s. So n is the dimension of the ambient space, k is the dimension of the subspace we're projecting onto, a is the dimension of the original set, and s is the dimension where things get exceptional, like the dimension below which the projection's dimension drops unexpectedly.
Okay, so sub-on k considers all of those and gives a lower bound on the dimension of the exceptional set. And they even provide a figure 1, to show how the function behaves.
Yeah, figure 1's a good way to visualize how sub changes as you change those parameters.
Okay, I think I'm starting to get a handle on this. So sub is really the key to their work. It lets them establish those tight bounds. But how do they actually go about proving these bounds? Like, what's their overall strategy?
Their proof is very clever, and it uses Mattila's projection theorem and Mattila's slicing theorem a lot. These theorems connect projections and cross-sections of sets in different dimensions, which allows them to kind of break down the n+1 dimensional problem into smaller n-dimensional pieces.
Interesting. So they're taking this complex higher dimensional problem and breaking it down into simpler parts.
That's right. And the key to their proof is in a series of lemmas 3.3 through 3.6.
So each of those tackles a different aspect of this process, and eventually they lead to those bounds for K1 and KN1.
Yes, exactly. Lemmas 3.3 and 3.4 deal with K1, and then 3.5 and 3.6 focus on KN1. Each lemma uses a combination of projections, slices, and dimensional reductions to relate the n+1 dimensional problem to an n-dimensional problem.
It sounds like a pretty intricate process. I would say I'm impressed by their approach. They're not just using equations, they're really using geometric intuition and powerful theorems.
I agree. Their work shows how powerful geometric thinking can be in math. It's not about just crunching numbers, it's about seeing the connections and patterns that explain these complex things.
All right. I'm ready to dive into those lemmas. But before we do that, can you remind me again, what's the main idea behind lemma 3.3?
Yeah, so lemma 3.3 is all about reducing the dimension of the problem. It says if you have an n+1 1AST pair, meaning you're in n+1 dimensional space projecting onto a line, and T is the dimension of the exceptional set, then you can also find a similar pair in n-dimensional space. Basically, if you can solve it in a lower dimension, you can kind of lift that solution back up.
Okay, so it's a divide and conquer strategy.
Exactly. And they do this by picking a specific hyperplane in the n+1 dimensional space. A hyperplane is just an n-dimensional subspace. It's like taking a slice of a cake.
Okay, I get that. But I guess not just any hyperplane will do, right? There must be some specific properties they need to make this work.
You're right. They have to choose the hyperplane carefully. Let's call it V. So first, when they project the original set A onto V, the projection needs to have the same Hausdorff dimension as A, which is A. They want to make sure they don't lose any information about the size of the set when they project it down.
So they're making sure this lower dimensional slice still represents the full complexity of the original set.
Yeah. And the second property is that this hyperplane has to contain a subset of those exceptional lines, E, and this subset has dimension just a tiny bit smaller than T. They call it T1.
Okay, so they need a hyperplane that not only preserves the dimension of the set, but also contains a good portion of those exceptional lines. But how do they know they can even find a hyperplane like that?
That's where they use Mattila's projection theorem and corollary 3.9. These guarantee they can always find a hyperplane that fits those two conditions.
Oh, corollary 3.9. Can you remind me what that was about?
Right. So corollary 3.9 says, if you have a set of lines in n-dimensional space with Hausdorff dimension E, there's always a hyperplane that contains a subset of those lines with dimension T1.
Okay, so it connects the dimension of a set of lines to the dimension of a subset in a lower dimensional space.
Exactly. And they use this corollary to make sure that their hyperplane contains a big enough portion of those exceptional lines.
Okay, so they've got this hyperplane V now. How does that actually help them prove lemma 3.3?
Well, they basically restrict the whole problem to that lower dimensional space. They look at the projection of A onto V, which they call A, and the subset of exceptional lines that lie within V, called E.
It's like they're focusing in on a specific part of the problem where they can analyze it more easily.
Right, and because they chose V so carefully, they know A still has dimension A, and E has dimension T1, which is a little less than T.
So they've created this new N1AST1 pair in n-dimensional space, which is exactly what they wanted.
Exactly. It's a great example of how you can use geometric reasoning to simplify a really complex problem.
Okay, so lemma 3.3 is all about reducing the dimension from n plus 1 to n. What about lemma 3.4? Is it similar?
It's also about dimensional reduction, but it looks at a slightly different situation where the dimension of the unexpected projection is less than or equal to A1, A being the dimension of the original set.
So they're looking at cases where the projection is like much smaller than the original set.
Right. And this time, instead of picking a hyperplane directly, they use Mattila's slicing theorem to find a specific slice of A, which they call A. This slice has dimension A1.
Okay, so this time they're not just reducing the dimension of the space, they're reducing the dimension of the set too.
Yeah, and then they show that if you take any line from the exceptional set E and you project both A and A onto that line, the projections will have the same dimension.
Wait, so even though A's is smaller, its projection has the same dimension as A's projection on those specific lines. That's kind of weird.
Yeah, it's a bit counterintuitive, but that's how these exceptional sets work. They behave in unexpected ways.
So they can replace A without really changing the problem because their projections are the same.
Exactly. And they use lemma 3.7, which comes from Mattila's projection theorem, to show that the projection of E onto the hyperplane containing A, they call it E, has dimension at least T, where T is at least as big as the minimum of T in N1.
I'm seeing a pattern here. They shrink both the set and the exceptional set, bring everything down a dimension, but they make sure the connection between them stays the same. And it gives them the N1A1AST pair.
You got it. They're very careful to make sure they don't lose any important information during this reduction.
This is so clever. We've talked about lemmas 3.3 and 3.4 for K1. Now lemmas 3.5 and 3.6 are for Kn1, right? And that's where they get those exact bounds.
That's right. And they use similar ideas about dimensional reduction and slicing, but with some new twists.
Okay, I'm ready. Tell me about lemma 3.5.
So in lemma 3.5, they have an n plus 1 NAST pair. So they've got a set in n plus 1 dimensional space, and they're projecting it onto an n-dimensional hyperplane and looking at the exceptional set where the dimension drops below a set.
Okay, so now we're talking about projections onto hyperplanes instead of just lines. That sounds more complicated.
It is a bit more complicated, but the basic idea is the same. They need to find a way to make the problem lower dimensional without losing any of the important information.
So how do they do that this time?
They use Mattila's projection theorem. That theorem tells us that for most n-dimensional hyperplanes, when you project the original set A onto that hyperplane, the dimension of that projection is the same as the dimension of A, which is A. So again, they make sure they don't lose any information about the size of the set when they project it.
Okay, so they pick their projection carefully to keep the dimension of the set. But what about that exceptional set, the one where the dimension drops?
Right. They use lemma 3.7 again. Remember, lemma 3.7 tells us that if you project a set of lines onto a hyperplane, the dimension of the projection is usually the minimum of the original dimension and the dimension of the hyperplane minus 1.
Ah, right. So they're using that to connect the dimension of the exceptional set in n plus 1 dimensional space to the dimension of its projection onto that hyperplane.
Exactly. And since they're working with hyperplanes, the dimension of the hyperplane minus 1 is just n1, which is the same as k in this case.
So it all works out perfectly. They can show that the projection of the exceptional set still has dimension at least t, which is the minimum of t and n1, and that gives them their n and 1 AST pair.
Exactly. They use those theorems very precisely to get the exact reduction they need.
Okay, this is great. Now, on to lemma 3.6. This is the lemma that really helps them prove those sharp bounds for kn1. What's special about this one?
This is where things get really neat. It starts the same way as lemma 3.5 with an n plus 1 NAST pair, a set in n plus 1 dimensions projected onto an n-dimensional hyperplane. But now they add a condition. A and AS and 2 all have to be bigger than 1.
So they're focusing on cases where the dimensions are all greater than 1. That must be important for getting those precise bounds.
It is. This is where they use corollary 3.9 again, but in a really clever way. Remember that corollary says if you have a set of lines with dimension t, you can find a hyperplane that contains a subset of those lines with dimension t1.
Yeah, it's like finding a smaller slice that still captures a lot of the original lines.
Exactly. But here's the trick. They apply this corollary not to the exceptional hyperplanes, but to the lines that are perpendicular to them.
Wait, so they're looking at the lines sticking out from the exceptional hyperplanes? I don't get why they would do that.
That's the really clever part. Because now they can use corollary 3.9 to find a hyperplane, we can call it V, that contains a bunch of those perpendicular lines with dimension t1, where t is almost as big as t.
Okay, so they have this hyperplane V. How does that relate back to those exceptional hyperplanes?
Here's the key. If a line is perpendicular to a hyperplane, and that line is inside V, then the original hyperplane has to intersect V too. It's just geometry.
Oh, I see. So they're using those perpendicular lines as a way to force those exceptional hyperplanes into their special hyperplane V.
Right. And then they use Mattila's slicing theorem again. This lets them find a copy of V, just shifted over a bit, so that its intersection with the set A has dimension A1. They call this intersection A sub X sub.
So they're not just using V, they're using a specific shifted version of V that cuts through A in a way that reduces the dimension of the set.
Exactly. And for the final step, they use Marstrand's vertical slicing theorem to look at the projections of A sub X sub onto those exceptional hyperplanes that intersect V.
They're really putting these theorems to work.
They are. And this theorem tells them that the dimension of those projections can't be bigger than S1.
So they've shrunk the dimension of the set, the dimension of the projection, and the dimension of the exceptional set all at once. By choosing that shifted hyperplane V plus X and looking at its intersections and projections.
You got it. It's a really neat trick. They've created an N, N1, A1, S1, T1 pair, just like they needed for lemma 3.6, and now they have everything they need to get those sharp bounds for K equals N1.
This is amazing. It's like they built this elaborate machine that combines all these theorems and lemmas to get those bounds.
It's really elegant work, but what's even more impressive is that they don't just stop at proving those bounds. They actually go and construct examples of sets that have those exact bounds.
So they're not just saying, here's the limit. They're showing us that it's possible to reach that limit.
Exactly. It shows how well they understand this topic.
Okay, we've covered a lot. I'm starting to see how impressive their work is. We've gone through these four lemmas, and now I want to see how they put it all together to get the complete proof.
I agree. It's time to see how all these pieces come together to create those sharp bounds. Are you ready to look at the final part of the proof?
Yeah, let's do it. All right, we've seen lemmas 3.3 to 3.6. They each handle a different piece of the problem. But how do they all fit together to get those upper bounds for the dimension of exceptional sets?
That's the key question. It's like having all the parts, but we need to put them together. They use mathematical induction for this.
Induction, right.
Yeah.
That's how mathematicians handle problems with an infinite number of cases. So what's their starting point? What's the base case?
They start with the easiest case, when n2. So we're working in 2 dimensions, and luckily we already know the upper bounds for that, thanks to Wren and Wang's theorem.
Okay, so they got the foundation. How do they go from n dimensions to n plus 1? It seems like it would get really complicated with all the different k and a and these values.
It does get complicated, but they're very systematic. First, they look at the case where k1. That means we're projecting our set onto a line in n plus 1 dimensional space.
Okay, so those projections where the dimension drops more than expected.
Right. They start with an n plus 1, 1 AST pair. That's the set in n plus 1 dimensions, the projection onto a line, and t is the dimension of that exceptional set.
Those cases where dimensions don't behave how we expect.
Exactly. Now, this is where those lemmas come in. Depending on the relationship between A, the dimension of the set, and S, the dimension of that unexpected projection, they use either lemma 3.3 or lemma 3.4.
So they're using those lemmas to connect the different dimensions. Those let us make an N1AST pair in n-dimensional space, right? So it's a simpler problem.
Exactly. They're saying if this upper bound is true in n dimensions, then it has to be true in n+1 dimensions because of these lemmas.
Like climbing a ladder one step at a time.
They use the lower dimensional result to understand the higher dimensional one.
But how do they actually connect them? How does knowing the bound in n dimensions help them in n+1?
They use induction. They assume the upper bound is true for n dimensions. That's part of how induction works. And then they can use that to control t in that n-dimensional pair they made.
Okay, so they use that assumption to understand t. How does that connect back to t, the dimension in the original problem?
That's the clever part about those lemmas. They keep the relationships between the sets and the projections and those exceptional sets the same when we change dimensions. So if we know something about t, we know something about t.
I see. So by figuring out t, they figure out t.
Exactly. It's a chain of logic. And they use the same idea when kn1, that's when they get those really good bounds. They use lemmas 3.5 and 3.6. Those were made specifically for those cases, remember?
Yeah, those were the ones where they carefully reduced the dimension while making sure all the important relationships stayed the same.
Exactly. It's the same logic. Start with the n+1 NAST pair. Use the right lemma, get an n1AST pair, use the induction assumption to understand t, and then use that to understand t in the n+1 dimensional problem.
It's a really neat process. Go down in dimension, use what you know, and then climb back up to the higher dimension.
Exactly. And this gets them those exact bounds for K1 and KN1. Not just some estimate, but the exact bounds. That's really impressive.
It feels like they really solved those cases completely. They figured out how big those exceptional sets can be. Do they talk about what's next?
Yeah, it's a great question. They solved those two cases, but there's still more to explore. What about all those other k values between 1 and n1? We know the bounds at the ends, but what about everything in between? Maybe there's a pattern, some formula that explains how these exceptional sets work for any nnk.
That's really interesting. It makes you wonder if there's some deeper connection between all these cases. It's like they've given us a map, but there's still so much to explore.
Exactly. And that's what's so cool about math. Every answer leads to more questions. This paper has given us new tools to understand this topic, and I bet it will lead to even more discoveries about these exceptional sets and projections.
I think that's a great place to wrap things up. We've covered a lot. We've looked at the basic ideas, the details of their proofs, and even thought about what's still unknown.
It has been a challenging but really interesting deep dive.
I completely agree. And maybe this will inspire someone listening to make the next big discovery. That's the great thing about curiosity. It can lead to amazing things.
Couldn't have said it better myself.
Until next time, keep those brains working and keep exploring the world of math. Welcome back, everyone. We're diving into something a little different today, a little more abstract. We're going to be exploring Hausdorff dimension and orthogonal projections.
Oh, yeah. Sounds fun.
I think it will be. And you already probably know this, but sometimes when you project a set onto a lower dimensional space, well, sometimes it loses some dimension. And that's kind of strange when you think about it.
Yeah, you'd think the dimension would just stay the same.
Exactly. Yeah. So that's what we're going to try and unpack today. Like, how does that happen? And how big can these exceptional sets where this dimension drop happens, how big can those actually be?
And we've got a great paper to help us out with that.
We do. We're looking at bounding the dimension of exceptional sets for orthogonal projections.
Kishy title.
Right. And it's by Scholek, Cernier, Lutz, Mirdomo, and Still.
Wow. Quite the team.
Yeah. Just from the author list, it's going to be dense.
Yeah.
But that's what we're here for. So before we get too far, can we just back up for a second? And you can remind us about Hausdorff dimension. I know it's a way to measure the size of sets, right? But it's not just our usual 1, 2, 3 dimensions, is it?
No, it's not. We're used to thinking about dimensions in whole numbers, right? Like a line's one-dimensional, a plane is two-dimensional.
Right.
But Hausdorff dimension, it lets us measure sets that are a bit more, how do I say this? intricate sets, like fractals. This can have fractional dimensions, you know.
Okay, so like more than a line, but less than a plane.
Exactly. It's a way to capture how rough or how complex a set is.
Okay, I'm with you so far. So this paper, it talks about these special sets called exceptional sets, right? Can you just set the scene for us? Like, what are they and why are they so interesting to mathematicians?
Sure. So there's this classic result called Marstrand's theorem. And imagine you have a set. Let's say it's in a plane, and you project it down onto a line. What Marstrand's theorem says is that for almost every direction you could project it, the Hausdorff dimension of that projection, that projected set, is going to be the minimum of, well, either the original set's dimension or 1.
Okay, so if you had a two-dimensional set, the projection would usually just be a line, right? One-dimensional.
Exactly. But here's the thing. The key word is almost every. Because there are these special directions where the dimension of the projection can drop even further.
Oh, interesting.
Yeah. And those are our exceptional sets.
Oh, so they're like the rule breakers of projections.
Aha, kind of.
And this paper is all about like figuring out how big these rule breakers can actually be.
That's right. And they introduced this function, TNKAS, which basically tells you the biggest possible dimension of the exceptional set.
Okay, and wait, what do all those letters stand for again?
So n is the dimension of the space we're working in, k is the dimension of the subspace we're projecting onto, a is the Hausdorff dimension of our original set, and s is the dimension of the projection, where we see that unexpected drop.
Okay, so TNKAS is like a detective telling us how much hiding space there is for these sneaky projections.
Ah, I like that. Yeah, that's a good way to think about it.
So what did mathematicians do before this paper to try and understand this TNKS function?
Well, there's some earlier work, like Mattila had some bounds on it. And then folks like Falconer, Perret, and Schlag, and Wren, they refined those bounds. But finding a really tight bound, like one that tells you the exact maximum dimension, that's been a tough nut to crack.
And that's where this paper comes in, right?
You got it.
They introduced this new function, SNKA, and they say this is a lower bound for TNKS.
Yeah, they're basically saying, hey, the exceptional set can't be smaller than this, and this SNKAS function gives you that minimum size.
Okay. But a lower bound is just a starting point, right? It doesn't tell us for sure that the exceptional sets are that big.
Right. There could be even bigger ones lurking out there.
So are there any cases where they know for sure how big those sets can get?
Actually, yeah. That's one of the cool things about this paper. They actually prove that in some cases, this SNKAS is not just a lower bound, it's also an upper bound, meaning they've found the exact maximum size.
Whoa, okay, so in those cases, they've totally solved it.
Yeah.
Which cases are those?
It happens when k equals 1, so when we're projecting onto just a line, and when k equals n minus 1, which is when we're projecting onto a hyperplane, you know, a subspace that's just one dimension lower than our space.
Okay, so for really simple projections, like onto a line, and those almost as big as we can get projections, they've got it figured out. I bet the proofs for that are pretty intense.
They are, but they're also really well structured, you know, like for the lower bound, they use this clever inductive argument. It starts with n equals 2 as the base case.
Oh, right, induction.
Yeah. And the key to making this induction work, it's these 4 observations. They relate the dimension of exceptional sets in n dimensions to the ones in n+1 dimensions.
Ooh, okay, so they're showing that if the lower bound holds in one dimension, it has to hold in the next one up, and so on. Can we talk about those observations a bit?
Yeah, definitely. So, like, observation 1, it basically says, if you have an exceptional set in n-1 dimensions, you can basically extend it up to n dimensions, and the projection doesn't change. Like, imagine taking a square and extruding it to make a cube.
Right, okay.
So the dimension of the exceptional set goes up, too, because now you have more room in that extra dimension.
Okay, so we're, like, lifting the exceptional set from a lower dimension to a higher one. Right. What about the second observation?
So observation 2, instead of extending the exceptional set, it looks at extending the original set that you're projecting. Like, take that square and stretch it out infinitely in the third dimension.
Okay, so now we're adding a dimension to the set we're projecting?
Exactly, and that can potentially lead to a bigger exceptional set when you project down.
And observation 3.
That one's about extending the subspace you're projecting onto. It's like taking our 2D plane and thickening it into a 3D space.
So instead of stretching the set, we're making the target of our projection bigger.
Exactly. And that gives you more directions where the projection could, like, collapse and give you a bigger exceptional set.
Okay, that makes sense. And then the last one?
Observation 4 is a bit more specific. It only applies when k equals n minus 1.
So when we're projecting onto a hyperplane.
Right, and it basically looks at how projections onto hyperplanes in n dimensions relate to the ones in n plus 1 dimensions.
So it's like connecting the exceptional sets across different dimensions, right?
Precisely, and the paper uses all 4 of these observations, along with that inductive structure, to build up the proof for the lower bound.
Wow. It's like a delicate dance of mathematical ideas.
Aha, that's a good way to put it.
My brain's already starting to hurt, but in a good way. So they've got this lower bound, and sometimes they even know the exact maximum size. How do they prove that S and K, AS, is also an upper bound in those special cases?
Well, for that, they use something called reverse induction.
Reverse induction, is that even allowed?
Yeah, it's like regular induction, but you start from the highest dimension and work your way down.
Huh, that's interesting.
To help with that, they use this thing called an NKAST pair. Have you heard of that?
Yeah, I think we mentioned it earlier. It's just a way to keep track of all those variables, right?
Right. So you have n, the dimension of the space, the n's of the subspace we're projecting onto, the Hausdorff dimension of the original set, S is the dimension where the projection drops, and T is the dimension of the exceptional set itself.
Yeah, I'm following.
So the idea is to show that if you have one of these pairs in, say, n plus 1 dimensions, you can always find a corresponding pair in n dimensions.
So you're basically saying if this dimension drop can happen in a higher dimension, it must also be happening in a lower dimension too.
Exactly. And they prove 4 lemmas that are like the reverse of those 4 observations we talked about earlier. It's like they're taking apart the inductive argument step by step to show how the upper bound follows.
Wow, that's really clever.
And by combining those lemmas with the reverse induction, they prove that for k equals 1 and k equals n minus 1, that SNKAS function, it's not just a lower bound, it's the exact maximum size of the exceptional set.
Okay. I'm starting to see how it all fits together now.
Yeah.
But I think I need a little visual aid to really solidify it in my head.
Oh yeah, visuals are always helpful. Remember that figure we talked about earlier, the one that visualizes the values of SNKAS for a specific case?
Yeah, the one with all the different regions?
Exactly. So picture this. You have this coordinate plane, and the horizontal axis is the Hausdorff dimension A of the original set. And the vertical axis is the dimensions where the projection drops. Now the plane is divided up into all these different regions, right? And each region has a different formula for SNKAS.
So the formula changes depending on where you are in this plane.
Yep. It depends on things like the floor and ceiling of AS and whether S is bigger or smaller than certain values.
Okay, so this visual helps us see how the lower bound changes based on the dimensions of the original set and the projection.
Right. It gives you a more concrete way to see how SNKS actually behaves. And it shows how complex this problem really is, right? All these different formulas controlling different parts of the parameter space.
I'm starting to understand why this paper is such a big deal. It's not just about proving theorems, it's about understanding how all these dimensions and projections interact with each other.
You got it. And remember, the paper goes even deeper, looking at those special cases where K1 and Km mid 1, and they actually find the exact maximum size of the exceptional set.
Right, those are the cases where SNKS is both a lower and an upper bound.
Exactly. And they use that reverse induction technique we talked about to prove it.
This is so cool. I can't wait to dive into the next part of the paper where they talk about the applications of this stuff.
Me too. It's amazing how these abstract concepts can actually have real-world uses.
Okay, well, let's take a short break, and then we'll come back and explore those applications.
Sounds good. All right, so you're ready to see how this math actually plays out in the real world?
Oh, yeah, definitely.
Yeah.
I'm curious how something as abstract as exceptional sets could have practical applications.
Well, let's think about image processing, like with digital images.
Hmm?
So a digital image, it's basically just a bunch of pixels, right? And you can think of each pixel as a point in like some high dimensional space.
Okay.
And each pixel has a color or an intensity value, and that's represented by coordinates in that space. Like if you have a black and white image, you'd only need a 2-dimensional space, right? 1 dimension for the horizontal position, 1 for the vertical. And then the coordinates of each point tell you how dark or light that pixel is.
Right. And for a color image, you'd need more dimensions to represent the different color channels.
Exactly. Now, imagine you want to compress that image, to store it more efficiently or to transmit it faster.
Mm-hmm.
One way to do that is to project that image data onto a lower dimensional space.
So you're basically reducing the number of dimensions you need to describe the image.
Yep. And hopefully you don't lose too much information in the process.
Right.
But this is where the exceptional sets come in. if you're unlucky and you choose a projection direction that happens to be, an exceptional set, you could lose more information than you expected. Like the dimension of the projected data could drop more than you intended.
Oh, so you could end up with a blurry or distorted image.
Exactly. So understanding these exceptional sets, it can help you avoid those bad projections.
I see, yeah. So you can choose a direction that preserves as much information as possible.
Right. And if you know the maximum size of those exceptional sets, you can design algorithms that are, less likely to run into those problems.
That's pretty cool. So we're using this really abstract math to make our image compression algorithms better.
Pretty much. And it's not just images, it's also relevant for data analysis.
Oh, okay. How so?
Well, in a lot of the data analysis, you're dealing with these huge data sets, right? Like tons of features or measurements for each data point.
Yeah, like genetic data or financial data.
Exactly. And you can think of each data point as, again, like a point in this high-dimensional space.
Just like with the pixels.
Yep. And a lot of times you want to reduce the dimensionality of that data to make it easier to visualize or to analyze.
Right.
So you might use techniques like principal component analysis or PCA or linear discriminant analysis.
I've heard of those.
Yeah, so those essentially project the data onto a lower dimensional space.
So again, we're trying to simplify things without losing too much information.
Exactly. But, you guessed it, those exceptional sets can cause problems here too.
Oh, I bet.
Because if your projection aligns with an exceptional set, you could end up with a representation of the data that doesn't really reflect the true relationships between things.
Right, like you could miss important patterns or draw wrong conclusions.
So the exceptional sets are kind of hiding the insights we're trying to find.
Haha, yeah, that's one way to think about it. So by understanding these sets, we can make our data analysis techniques more robust. Choose projections that are more likely to preserve the important structure of the data.
Okay, this is blowing my mind a little bit. I never would have thought that Hausdorff dimension and all this stuff would be connected to image processing and data analysis.
Yeah, it's a great example of how pure math can lead to unexpected applications.
All right, well, I think I'm ready to tackle those proofs now. Let's get into the nitty-gritty of this paper.
Okay, let's do it. It really does, doesn't it? It makes you wonder how much we don't know.
I know, right? And in this case, we've still got a lot to learn about these exceptional sets. Yeah, this paper gives us a great starting point. They found a lower bound on the size and even the exact maximum size for certain cases. But that general case, where you're projecting onto any dimension k, that's still wide open.
It's like they've given us a flashlight, but we're still in a huge, dark cave.
Yeah.
What do you think it'll take to solve that general case?
Oh, that's a tough one. I'm sure it'll involve a lot of creativity, some really good geometric intuition, and probably some new techniques that we haven't even thought of yet.
Yeah, maybe one of our listeners will figure it out. They're the experts, aren't they?
You never know. It's a fascinating problem, and who knows what kind of applications it could have.
Oh, yeah. Imagine if we could make even better algorithms for image processing, data analysis, all that stuff.
Right? Think about more efficient data storage, maybe even more accurate medical diagnoses, all because we understand these exceptional sets better.
Wow, that's amazing. Well, I think we've covered a lot of ground today.
Yeah, we really went deep on this one.
For those of you who want to keep exploring, the full paper is out there. Go check it out, see if you can crack the code on that general case.
Good luck.
And for everyone else, thanks for joining us on this deep dive. Until next time, keep those mathematical minds working.
See ya.
Welcome back, everyone. Ready for another deep dive.
Always excited to delve into some fascinating math.
Today, we're going to be tackling something pretty intricate.
Oh, do tell.
It's all about the dimension of exceptional sets in orthogonal projections.
Now that sounds like a mouthful.
It is. It is. But think of it like this. Imagine you're shining a light on a 3D object.
Okay, I can picture that.
And you're looking at the shadow it casts.
Right, the shadow. Got it.
That shadow, that's like a projection. But sometimes the shadow doesn't capture all the information about the original object, right?
Yeah, that makes sense. Like you lose some of the depth information.
Exactly. And these exceptional sets, well, they're like the places where those projections behave unexpectedly, where they don't quite tell the whole story.
Interesting. So mathematicians have been trying to figure out just how big these sets can get.
Exactly. For decades, they've been wrestling with this question.
It's like a mathematical mystery.
It is. And to help us unravel this mystery, we're diving into a paper today called Bounding the Dimension of Exceptional Sets for Orthogonal Projections.
Catchy title. Who are the authors?
It's by Cholak, Cernier, Lutz, Mayordomo, and Stoll. Quite a team.
Wow, a whole team of mathematicians tackling this problem.
Before we jump into the specifics of the paper, though, it's important to remember that this work builds on a legacy of other mathematicians.
Oh, absolutely. People like Marstrand and Kaufman, they did some groundbreaking work in this area, right?
Exactly. They really laid the foundation for understanding these projection problems.
And their work paved the way for others to make even more progress.
Absolutely. We can't forget about the more recent breakthrough by Ren and Wang, who proved Oberlin's conjecture.
Oh, that was a huge moment in the field, wasn't it?
A real aha moment.
Their proof provided some key insights that really advanced our understanding of these projections.
So let's get to the heart of this paper. It's tackling a pretty fundamental question. If you have a set in a higher dimensional space and project it onto a lower dimensional subspace, how often does that projection have a smaller dimension than you would expect?
Right, so it's going back to that idea that sometimes the shadow doesn't tell the whole story.
Exactly. And to explore this question, the paper introduces a few key definitions.
Ah, the building blocks of the mathematics.
The first one is GK, which represents all the possible k-dimensional subspaces within an n-dimensional space.
Okay, so if we were talking about 3D space, G32 would be all the different planes we could have within that space.
Exactly, you got it.
Makes sense. What's the next key definition?
Yet we have V, which represents the orthogonal projection onto a specific subspace, V.
So that's like actually creating the shadow, so to speak.
Precisely. Shining the light and seeing where it falls on that particular plane.
Gotcha. So what about those exceptional sets we talked about earlier? How do they define those?
They use T and KAS to represent the maximum possible dimension of that exceptional set. You know, those instances where the projection's dimension is smaller than expected.
So TNKAS is telling us how big that set of unexpected projections can be.
Exactly.
And is there a way to actually calculate or bound that value?
Well, that's where another function comes in, SKAS. The paper introduces this as a potential bound on T and KAS.
A potential bound. So they're trying to figure out if SEAAAS can tell us something about the size of these exceptional sets.
Exactly.
Fascinating. I'm already intrigued.
And you know what's really cool? They actually provide a visual representation of SAS in figure 1 of the paper.
Now that's helpful. Visualizing these abstract concepts can be so useful.
I know. It's a really neat diagram that shows how the size of the exceptional set changes as we tweak the different dimensions involved.
So we can actually see how SAS behaves as we adjust those parameters.
Exactly.
That's a great way to get an intuitive feel for what it represents. So what are the main things the authors are trying to prove about this SMPAS function?
Well, they focus on two key results. First, they prove that SAAS is always a lower bound for TKAS.
Meaning that the exceptional set can't be any smaller than what SAS describes.
Exactly. It's like setting a minimum size limit.
Okay, that makes sense. And what's the second result?
The second result is even more exciting. They show that when projecting onto a line where K1, or a hyperplane, where KN1, SNKAS, is actually equal to TNAS.
Wow. So they found a precise tight bound for those specific cases.
Exactly. It's like solving a puzzle that mathematicians have been working on for years.
That's a significant breakthrough. How did they manage to prove these results? What techniques did they use?
Well, they employed a clever combination of techniques: induction, projection theorems, and slicing theorems.
Sounds like a powerful mathematical toolbox.
It is. And they use these tools to meticulously construct their proofs step by step.
It's like building a delicate structure, piece by piece.
Exactly.
I'm eager to hear more about how they actually put these techniques into practice.
Me too. But before we get into the nitty-gritty of the proofs, let's take a quick break. We'll dive into those details in part 2 of our deep dives.
Okay, so where were we? Ah, yes, about to get into the nitty-gritty of the proofs.
Right. You ready to roll up our sleeves and dive in?
Absolutely. I'm curious to see how they actually use these tools like induction and slicing theorems.
Well, let's start with the lower bound proof, where they show that TNKAIS is always at least as big as STRAKS.
Okay, that's the one that sets the minimum size for these exceptional sets, right?
Exactly. And they start by establishing a base case, where N2...
Makes sense. Start simple and build up.
Right. And for this base case, they rely on a result from Ren and Wang's work, which they cite as theorem 1.1 in their paper.
Oh, I see. So they are building upon that earlier breakthrough we mentioned.
Precisely. That theorem provides a foundation for their argument.
So how do they go from that base case to higher dimensions?
Induction. It's like a domino effect. They show that if the lower bound holds in n dimensions, it must also hold in n+1 dimensions.
Ah, clever. So they are kind of like bootstrapping their way up to higher dimensions.
Exactly. They demonstrate that if you have a set with a certain exceptional set in n dimensions, you can construct a set in n+1 dimensions with an exceptional set that's at least as large.
So they are showing that this lower bound holds no matter how high you go in dimensions.
That's the idea.
Very elegant. Now what about that upper bound proof, the one where SARS, is actually equal to T in NKS for certain cases?
Ah, yes. That's where things get really interesting. They use a reverse approach compared to the lower bound proof.
Reverse approach? I'm intrigued. Tell me more.
Remember how in the lower bound proof they build up the argument from lower dimensions to higher dimensions?
Right, like building a tower from the ground up.
Exactly.
Mm.
Well, for the upper bound, they work in reverse. They start by assuming they have a set, and its exceptional set, in a higher dimension.
Okay, so they start at the top of the tower this time.
Exactly. And then they demonstrate that you can always construct a corresponding set and exceptional set in a lower dimension where the exceptional set is no bigger.
So they're essentially showing that if you have a certain size exceptional set in a higher dimension, you can't have a larger one when you project down to a lower dimension.
Precisely. It's like showing that the shadow can't be bigger than the object itself.
Uh-huh. That makes sense. But how do they actually make this reverse construction work? Seems tricky.
That's where those 4 key lemmas come in 3.3 through 3.6.
Oh, right, the lemmas. Each one tackles a specific case, right?
Exactly. And they are carefully designed to link that upper bound in higher dimensions to the upper bound in lower dimensions.
So it's like they are building a bridge between those different dimensions, making sure the bounds hold true all the way across?
A perfect analogy. And it's really remarkable how each lemma sort of undoes the constructions used in the lower bound proof to get back to those lower dimensions.
So the two parts of the proof are really intertwined.
Clever. Now, before we jump into each lemma, let's take a moment to clarify what these NKA-AST pairs actually represent. It's easy to get lost in the notation.
Good point. It's always helpful to ground ourselves in what these symbols actually mean.
So an NK-AST pair basically describes a specific scenario in our problem. N is the dimension of the space we're working in. K is the dimension of the subspace we're projecting onto. A is the Hausdorff dimension of the set we're projecting. S is the target dimension we expect the projection to have. And T is the dimension of that exceptional set where things don't behave as expected.
Okay, got it. So each lemma is essentially proving that if you have an N+1 KAST pair, you can always find a corresponding NKST pair where the dimension of the exceptional set T is less than or equal to T.
Exactly.
It's like saying that the weirdness of those exceptional sets doesn't get amplified as we go to lower dimensions.
Well put. Okay, ready to tackle lemma 3.3.
Bring it on.
All right. So this lemma deals with projections onto a line, which means K1. And remember, it's all about showing that if you have a specific situation in n+1 dimensions, you can find a corresponding situation in n dimensions where the dimension of the exceptional set hasn't grown.
Right. Keep that exceptional set in check. So how do they go about it?
They start by picturing a subset of Rn+1, which they call A, with Hausdorff dimension A.
Okay, so that's our set we're going to project.
Exactly. And then they consider all the different ways to project this set onto a line.
All the possible lines within that higher dimensional space.
Right. And they call this set of all possible projections G1, 1, 1.
Okay, so we've got our set A, and we're looking at all the ways to shine a light on it and get a line-shaped shadow.
Perfect. Now, the exceptional set, those projections where the dimension drops unexpectedly, they call that E.
So E is like the set of all those wonky shadows.
Exactly. And they assume E has a Hausdorff dimension of T.
Okay, so T is measuring how big that set of wonky shadows is.
You got it. And now comes the clever part. They use Mattila's projection theorem to find a hyperplane.
A hyperplane, like a slice through that higher dimensional space.
Exactly. And they call this hyperplane V.
Okay, so they're slicing through this space with V. What's so special about this particular hyperplane?
Well, they choose it very carefully so that the Hausdorff dimension of the intersection of A and V is A1.
Ah, so they are choosing the hyperplane so that it slices through set A in a way that reduces the dimension by 1.
Precisely. But there's more. They also make sure that this V slices through the exceptional set E in a similar way.
Wait, so they are making sure that the hyperplane reduces the dimension of both A and E.
Exactly. They ensure that the Hausdorff dimension of the intersection of E and V is T1.
Clever.
Yeah.
They're controlling how that hyperplane slices through both sets.
Right. And then they project everything down onto this carefully chosen hyperplane V.
They are basically shrinking the whole problem down a dimension.
That's a great way to put it. And because they were so strategic in choosing V, the Hausdorff dimensions behave nicely.
Meaning they get the N1, A1, ST1 pair they were looking for.
You got it. They've successfully shown that they can go from a situation in n+1 dimensions to a corresponding situation in n dimensions without that exceptional set getting any bigger.
It's like they've tamed those wonky shadows, kept them under control.
A perfect analogy.
So that's lemma 3.3. What about 3.4? Does it follow a similar logic?
It does, but with a little twist. It still focuses on projections onto a line, but it deals with a specific case where the Hausdorff dimension of set A is exactly one more than the target dimension S.
Okay, so they are focusing on a scenario where they know the projection is going to reduce the dimension by 1.
Exactly. And instead of using a hyperplane directly to slice through the set, they use a translate of a hyperplane.
A translate? That's just shifting the hyperplane over a bit, right? Why do they need to do that?
It's all about ensuring those dimensions line up correctly. If they used a hyperplane directly, they couldn't guarantee that the intersection with set A would have the right Hausdorff dimension.
I see. The translate gives them more control over where that slice happens.
Exactly. And once they've sliced things up with that carefully positioned translate, they proceed much like they did in lemma 3.3.
They project everything down to that hyperplane and show that the exceptional set hasn't grown.
You got it. They've successfully shown that even in this specific scenario, that upper bound holds true.
It's all coming together. They are really building a solid argument here.
They are. And remember, we still have 2 more lemmas to go.
Oh, right. We've tackled the line projections. Now we need to move on to those hyperplane projections.
Precisely. So ready for lemma 3.5?
Absolutely. Let's hear it.
All right. This lemma focuses on projections onto a hyperplane where the k in 1, but specifically for cases where the target dimension S is less than or equal to n1.
So we are projecting onto a hyperplane, and we are expecting some dimension reduction because the target dimension is smaller than the hyperplane itself.
Exactly.
Okay, I'm following so far. Now, how do they approach the proof in this case?
Well, they start by making a very strategic choice. They choose a hyperplane that is actually part of the exceptional set E.
Wait, they are choosing a hyperplane from within the exceptional set? Isn't that going to make things more complicated?
It might seem that way at first, but remember, the exceptional set contains those projections where the dimension drops unexpectedly. So by starting with a hyperplane that's already in E, they guarantee that the projection of set A onto that hyperplane will have a dimension less than E's.
Ah, I see. They're sort of using the exceptional set to their advantage.
Exactly. It's like saying, if we want a projection that has a smaller dimension, let's start with one that we know already has that property.
Clever. It's like they're turning the problem on its head.
Exactly. And once they've got this hyperplane chosen, they can use lemma 3.7 to show that the dimension of the exceptional set itself also reduces in the process.
So they're projecting everything down onto the special hyperplane from E, and it all lines up perfectly. The exceptional set doesn't get any bigger.
Exactly. And that's how they prove lemma 3.5.
Another elegant piece of the puzzle.
Now, are you ready for the final lemma, lemma 3.6?
Hit me with it.
Right. This one also deals with projections onto a hyperplane where kn1, but this time the target dimension S is greater than n1.
Okay, so now we are projecting onto a hyperplane, but the target dimension is actually bigger than the hyperplane itself.
Precisely. So we are not necessarily expecting the dimension to shrink just from the projection alone.
Right, because the target dimension is bigger than the space we are projecting onto.
Exactly. And to tackle this case, they turn to corollary 3.9.
Now, what does this corollary tell us?
It allows them to find a very specific hyperplane, one that contains a subset of the exceptional set with a particular dimension.
So again, they're being very strategic about which hyperplane they choose, not just any hyperplane will do.
Precisely. And they use this carefully chosen hyperplane along with another powerful tool, Mattila's slicing theorem.
Ah, Mattila's slicing theorem. I remember that one from our earlier discussions. It's all about finding those strategic slices, right?
You got it. And they use this theorem to find a translate of their chosen hyperplane. Remember, a translate just means shifting it over a bit.
Right, without changing its orientation.
Exactly. And this translate intersects set A in just the right way to reduce its dimension.
So they are using this translate to slice through set A and shrink it down.
Exactly. And by combining corollary 3.9 and Mattila's slicing theorem, they could show that the exceptional set shrinks as well.
It's like they are performing a delicate surgery on those dimensions, making sure everything lines up just right.
A perfect analogy. And that, my friend, is how they prove lemma 3.6.
Wow, we've really gone through the whole proof structure now.
We have, from the lower bound to the upper bound, and all 4 of those intricate lemmas.
I feel like I have a much deeper understanding of how they built their argument.
Me too. But you know what? We haven't even talked about the detailed proofs of those lemmas yet. They go through each one step by step, showing all the calculations and justifications.
There's even more to explore.
Oh, yeah. But I think we've covered enough for this episode.
That's probably a good place to stop for now. It's a lot to take in. All right, ready to dive into those detailed proofs.
Let's do it. I'm really curious to see how they actually lay everything out step by step.
Me too. It's one thing to understand the general strategy, but the real magic is in the details.
Yeah, absolutely. So let's start with lemma 3.3. Just to refresh our memories, this lemma deals with projections onto a line, so K1.
Right, and it's all about connecting a scenario in n+1 dimensions to a corresponding scenario in n dimensions.
Exactly. And showing that that exceptional set doesn't get any bigger as we move down in dimensions.
Okay, so how do they actually go about proving this?
Well, they start by considering a specific subset of Rn plus 1, they call it A.
Okay, so A is our set in n+1 dimensional space.
And it has a Hausdorff dimension of A.
Right, A for the dimension of set A. Makes sense.
Now, they want to look at all the possible ways to project this set A onto different lines within that n+1 dimensional space.
So all the possible shadows of A, but just the ones that are lines.
Exactly. And they denote this set of all possible line projections as Gn plus 11.
Okay, so we've got our set A, and we're looking at all the ways it can cast a shadow that's a line. What's next?
Now they introduce E, which represents the exceptional set. Remember, that's the set of all those line projections where the Hausdorff dimension drops unexpectedly.
Right, those wonky shadows where we lose some information.
Precisely. And they assume that this exceptional set E has a Hausdorff dimension of T.
Okay, so T is measuring how big that set of wonky shadows is.
Exactly. Now, here's where they start to work their magic. They bring in Mattila's projection theorem.
Ah, that powerful theorem that lets them find just the right slice through the space.
Exactly. And using this theorem, they can find a hyperplane, which they call V.
A hyperplane. So they're basically slicing through that n+1 dimensional space with V.
And they choose this V very carefully, making sure that it intersects set A in just the right way.
So the intersection of A and V will have a specific Hausdorff dimension.
Precisely. They ensure that the Hausdorff dimension of that intersection is A1.
Ah, so they've sliced through set A in a way that reduces the dimension by 1.
Exactly. But that's not all. They also make sure that V slices through the exceptional set E in a similar way.
Wait, so they are controlling how V intersects both A and E?
That's right. They ensure that the Hausdorff dimension of the intersection of E and V is T1.
Clever. They're making sure that V reduces the dimension of both sets in a consistent way.
Now, with this carefully chosen hyperplane V, they can project everything down onto it.
So they project set A onto V, and they project the exceptional set E onto V.
Exactly. And because they were so careful in choosing V, those Hausdorff dimensions behave just as they need them to.
Meaning the projection of A onto V has Hausdorff dimension A1, and the projection of E onto V has Hausdorff dimension T1.
Precisely. And just like that, they've created an N1A1 ST1.
Which is exactly what they needed to prove lemma 3.3.
Right. They've shown that you can go from a scenario in n+1 dimensions to a matching scenario in n dimensions, and that exceptional set hasn't gotten any bigger.
Very elegant. They really make it seem so simple.
Well, it might seem simple now that we see the logic, but it definitely took some clever thinking to figure this all out.
Absolutely. So on to lemma 3.4. What's different about this one?
It also deals with projections onto a line, but it focuses on a specific case where the Hausdorff dimension of set A is exactly 1 greater than the target dimensions S.
Okay, so in this case, we know the projection onto the line is going to reduce the dimension by 1.
Exactly. But instead of using a hyperplane directly to slice through the set, they use a translate of a hyperplane.
A translate? That just means shifting the hyperplane over?
Right, right. And they do this because they need to make sure that when they slice through set A, the intersection has the right Hausdorff dimension. Using a translate gives them the flexibility to find just the right position for that slice.
I see. So it's a subtle adjustment to ensure everything lines up perfectly.
And once they've made that slice with the translate, they proceed in a similar way to lemma 3.3. They project everything down onto that hyperplane.
And because they were so careful with how they sliced things, the exceptional set doesn't grow in the process.
You got it. They've successfully proven the lemma for this specific case as well.
Okay, so they've handled the line projections. Now for the hyperplane projections, right?
You got it. Lemma 3.5 tackles projections onto a hyperplane where kn1, but specifically for cases where the target dimension s is less than or equal to n1.
So we're projecting onto a hyperplane, and we're expecting some dimension reduction because the target dimension is smaller than the hyperplane itself.
Precisely. And to prove this lemma, they use a really clever trick. They choose a hyperplane that's actually part of the exceptional set E.
Wait, they choose a hyperplane from within the exceptional set. Why would they do that?
It might seem counterintuitive, but remember that the exceptional set contains those projections where the dimension drops unexpectedly. So if they start with a hyperplane that's already in E, they know the projection of set A onto that hyperplane will have a dimension that's smaller than A.
Ah, I see. They're using the exceptional set to their advantage. It's like saying, hey, if we want a projection that already has a reduced dimension, let's start with one that we know has that property.
Exactly. And by making this clever choice, they can then use lemma 3.7 to show that the dimension of the exceptional set itself also reduces in the process.
So by strategically choosing the hyperplane, they ensure that everything behaves just as they need it to. The exceptional set doesn't grow.
Exactly.
Okay, that's lemma 3.5. Now for the final piece of the puzzle, lemma 3.6. What's the challenge in this one?
This one also deals with projections onto a hyperplane where kn1, but this time the target dimension s is actually greater than n1.
Okay, so now we're projecting onto a hyperplane, but we don't necessarily expect the dimension to reduce because the target dimension is bigger than the hyperplane itself.
Exactly. And to tackle this case, they bring in corollary 3.9.
Now, what does this corollary allow them to do?
It helps them find a hyperplane that contains a subset of the exceptional set with a very specific dimension.
So again, they're carefully choosing their hyperplane, making sure it has this specific relationship with the exceptional set.
And they combine this carefully chosen hyperplane with Mattila's slicing theorem.
Ah, that handy theorem for finding those strategic slices.
They use it to find a translate of their chosen hyperplane.
Right, a translate just means shifting it over without changing the orientation.
And this translate intersects set A in a way that reduces its dimension.
So they're using the translate to carefully shrink set A.
And by combining the corollary and the slicing theorem, they can show that this construction also leads to a reduction in the dimension of the exceptional set.
It's all connected. By making these careful choices and applying these theorems strategically, they're able to show that even in this tricky case, the exceptional set doesn't get any bigger.
You've got it. And with that, they've proven all four lemmas.
And with those lemmas proven, the main result of the paper follows quite naturally.
Exactly.
Ugh.
They've successfully shown that those bounds on the dimension of exceptional sets hold true, both for projections onto lines and for projections onto hyperplanes.
It's a really beautiful piece of mathematical work. I'm impressed by their ingenuity and the elegance of their approach.
Me too. It's a reminder that even in the most abstract realms of math, there's a deep beauty and elegance to be found.
Absolutely. And it makes you wonder what other mysteries are out there waiting to be uncovered? What other elegant proofs are waiting to be discovered?
It's exciting to think about all the possibilities. Well, on that note, I think it's time for us to wrap up this deep dive.
Yes, I think we've covered a lot of ground today.
We have. And I want to thank everyone for joining us on this mathematical adventure. We hope you enjoyed exploring the intricacies of these exceptional sets with us. Until next time. Welcome back, everyone. Ready for another deep dive?
Always.
Today, we're going to tackle Hausdorff dimension and orthogonal projections.
Sounds fun.
Yeah, we're diving into a research paper called Bounding the Dimension of Exceptional Sets for Orthogonal Projections.
Okay, so we're looking at how much a set's dimension shrinks, right?
Exactly. When it's projected onto lower dimensional spaces.
Cool. So like how a 3D object casts a 2D shadow.
Yeah, that's a good way to think about it.
Yeah.
But it gets pretty complex.
Oh, I bet. Projections aren't always so straightforward.
Right. And the paper starts by looking at just that, orthogonal projections.
Okay, makes sense.
They use this notation, VA, for the projection of set A onto subspace V.
So like shining a light and looking at the shadow?
Exactly. But sometimes the shadow, or the projection, has a much lower dimension than you'd expect.
Interesting. Why does that happen?
But that's where the idea of exceptional sets comes in.
Okay, I'm listening.
So there's this theorem, Marstrand's theorem, which says that for almost every projection, the dimension reduction happens in a predictable way. But then there's this set of projections, the exceptional set, where the rule doesn't work.
So that's where things get tricky.
Exactly. And they denote that set as SA. And the big question this paper tries to answer is, how big can this exceptional set actually get?
I see. So they're trying to put some bounds on this weirdness.
Yep. And it turns out this question's been around for a while. Like, a lot of mathematicians have tried to figure this out.
Makes sense. It's a fundamental question about dimensions and projections.
Yeah. And the paper's introduction actually talks about some of those key attempts. It's like a history lesson in math.
Cool. Who are some of the big names involved?
Well, you've got Kaufman, Oberlin, Falconer,
Oh, yeah, I know some of their work.
and more recently, Wren and Wang. They all had their own contributions to the problem.
So it's been a collaborative effort over time,
Yeah, each one kind of built on what the others had done before.
slowly chipping away at the problem.
Exactly. And a big breakthrough came with Wren and Wang, actually. They proved Oberlin's conjecture, but just for the two-dimensional case.
Wow, that's a big deal.
Right. And that leads to theorem 1.1 in the paper. It gives a precise formula for the dimension of the exceptional set, but again, just in two dimensions.
Okay, so they've nailed it down for 2D, but what about higher dimensions?
Yeah, that's where it gets even more complicated, and that's what the paper really dives into.
I bet. So how do they even approach that?
Well, they introduced this function, TNONKAS.
Okay, and what does that represent?
It represents the largest possible dimension of the exceptional set.
Right, but in higher dimensions, I assume.
Yes,
Ugh.
when you project from n dimensions down to 8 dimensions.
Okay, starting to get the picture. But I'm guessing finding the exact value for that function is pretty tough.
You guessed it. It's really challenging. So instead of trying to find the exact value, they focus on finding upper and lower bounds for it.
That makes sense, kind of like boxing it in.
Yeah, exactly. So to get a lower bound, they introduce another function.
Of course they do.
It's called SAAETA. This is in definition 1.2.
Okay, another function to keep track of. What's special about this one?
Well, it acts as a lower bound for that first function, TNKAS.
Right, so it tells us the exceptional set can't be smaller than this.
Precisely. But this function is, it's a bit of a mouthful. It uses floor and ceiling functions, and it have all these variables.
Sounds intimidating.
Yeah, it can be a bit much to take in at first, but basically it captures how the different dimensions relate to each other.
The original dimension, the target dimension, the dimension of the set.
Exactly. And then S is like a threshold for how much the dimension can be reduced.
Okay, I'm following so far. But I could definitely use a visual to help wrap my head around this.
Well, you're in luck. The paper actually has a figure, figure 1, that shows what SNAAS.
Oh, Pertti, what kind of example do they use?
They take N10 and K3, so projecting from 10 dimensions down to 3. And it's really interesting to see how the function changes across different regions.
So we can actually visualize how this lower bound behaves.
Exactly. And the really cool thing is they don't just propose this lower bound, they actually prove that it's tight in two very important cases.
Oh, wow. So they're saying it's the best possible lower bound in those cases.
Yeah. And that's theorem 1.3. It says that SUTS, K-A-S, is tight when projecting onto a line, so in K1.
Right, just squeezing it down to one dimension.
And also when projecting onto a hyperplane, which is when KN1.
So almost all the way down, just one dimension less than the original.
Exactly. And they prove this using induction.
A classic. Love a good induction proof.
Right. It's a really neat way to show that something holds for all values.
So how does the induction work in this case? What's their base case?
Well, luckily they can start with N2, thanks to Wren and Wang's work. They already proved it for that case.
Okay, so they have a solid starting point.
Right. And then they assume the statement is true for some n, and they show that it must also be true for n plus 1.
Ah, the classic induction step. So how do they make that leap from n to n plus 1? It can't be that easy, right?
Well, it does involve a few tricks. They introduce a bunch of lemmas to help them along the way.
Lemmas. Okay, let's hear about those. What are they and how do they help?
Yeah, so these lemmas, there are 4 of them actually, and they're like the building blocks for proving those upper bounds in theorem 1.3.
Got it. So they're kind of breaking down the problem into smaller, more manageable chunks.
Exactly. And each lemma uses some pretty powerful tools from geometric measure theory.
Oh, fancy. Like what?
Well, lemma 3.3 uses Mattila's projection theorem. Have you heard of that one?
Yeah, I think so. It's about finding a projection that doesn't mess up the dimension too much, right?
Exactly. So in this case, they use it to find a hyperplane where when they project the original set onto it, they don't lose too much dimension.
Okay, that makes sense. But what about the exceptional set? We're trying to bound that dimension.
Right. And that's where corollary 3.9 comes in.
Another theorem. Okay, tell me more.
So this corollary guarantees that they can find a hyperplane where when they slice the exceptional set within that hyperplane, its dimension goes down to T1.
Wait, so they're slicing the exceptional set. I thought we were projecting it.
We are, but they're doing both. They're finding a hyperplane that works for both the projection and the slicing.
Whoa, okay, that's pretty clever. So they're kind of killing two birds with one stone.
Yeah, exactly. And lemma 3.4 takes a slightly different approach.
Yeah.
This time, they focus on reducing the dimension of the original set, the set A.
Okay, how do they do that?
They carefully choose a hyperplane and take a slice of the set within that hyperplane.
So it's like they're shrinking the set itself before they even start projecting.
Yeah, you could think of it that way. And the whole point is to get down to a lower dimension where they can use the induction hypothesis.
Ah, right, because they already know it works for N2.
Exactly. So both lemma 3.3 and lemma 3.4 are all about setting things up so they can apply the induction hypothesis.
Makes sense. It's like they're strategically maneuvering the problem into a position where they know they can win.
Yep, exactly. Now, lemmas 3.5 and 3.6, these deal with the case where we're projecting onto a hyperplane.
Okay, so KN1 in this case.
Right. Lemma 3.5, again, uses this idea of finding a well-behaved hyperplane.
So similar to lemma 3.3.
Kind of. But this time, the goal is to connect the dimension of the exceptional set in n+1 dimensions to the dimension of the exceptional set in n dimensions.
Okay, so they're linking the problem in a higher dimension to the problem in a lower dimension.
Exactly. It's all about connecting the dots between different dimensions. But lemma 3.6, this one's a bit more involved.
Uh-oh, more complexity. Bring it on.
Okay, so this one uses Marstrand's vertical slicing theorem.
Haven't heard of that one. What's that about?
It's a really cool theorem that basically tells you how a set's dimension changes when you slice it with a hyperplane.
Interesting. So they're using it to analyze those slices we were talking about earlier.
Exactly. And with this theorem, they're able to show that if you have what they call an n+1 NAST pair.
Okay, a lot of variables there.
Yeah, sorry. But basically it means you have a set in n+1 dimensions, and you're projecting it onto a hyperplane in n dimensions. And they show that if you have this kind of pair, then you can construct what they call an N1A1 S1 T1 pair.
Wow, okay, so they're not just reducing the dimension of the space, but also the dimensions of the set and the exceptional set. It's like a multi-dimensional compression algorithm or something.
Exactly. It's a really clever way to connect the problem in one dimension to the problem in a lower dimension, but with everything shrunk down.
Okay, that's pretty mind-blowing. So with these four lemmas in their toolkit, they're ready to tackle the proof of theorem 1.3, right?
Right. And the proof itself is a bit long and technical, but it basically uses induction and divides the problem into several cases, depending on the values of A and S.
So they have to consider different scenarios for how the dimension of the set and the threshold for dimension reduction play together.
Exactly. And for each case, they use the appropriate lemma to reduce the problem to a lower dimension, and then they use the induction hypothesis to prove the inequality.
Ah, so it all comes together beautifully. Each lemma plays its part in this grand scheme.
Yeah. And it really highlights the power of mathematical reasoning, how you can break down a complex problem into smaller steps and use logical arguments to build up a complete proof.
Absolutely. It's like a carefully constructed puzzle where each piece fits perfectly into place. And beyond the elegance of the proof itself, the results of this paper are pretty profound, right? I mean, they give us a much deeper understanding of how dimensions behave under projections.
Yeah, it's amazing to think how this seemingly abstract mathematical problem could have real-world implications in fields like signal processing or data compression.
Exactly. Anytime you're dealing with projections and dimensionality reduction, these results could be relevant.
It's really cool to see how these theoretical results can connect to the real world. But I'm curious, where do we go from here? Are there any open questions or next steps that come out of this work?
Oh, absolutely. There's always more to explore in math. One thing that jumps out is the fact that they only focused on orthogonal projections.
Yeah, that's true. What about other types of projections?
Right. So a natural next step would be to see if similar bounds can be found for non-orthogonal projections. That would make these results applicable to a much wider range of problems.
That makes sense. It's like they've opened up a whole new area of investigation.
Exactly. And even within the realm of orthogonal projections, there's still room for improvement.
Oh, how so?
Well, maybe they could find even tighter bounds for certain cases, or come up with completely different proof techniques that lead to new insights.
So the quest for better bounds continues.
Always. And on the computational side, it would be great to have efficient algorithms for calculating or approximating these bounds. That would make them much more useful for people working in other fields.
Yeah, it's one thing to have these theoretical results, but it's another thing to actually be able to use them in practice.
Exactly. And it's that bridge between theory and practice that often leads to the most exciting breakthroughs.
It's been a fascinating journey diving deep into this paper. It's really amazing to see how human curiosity and the power of mathematical reasoning can lead to such profound insights.
I agree. This deep dive into bounding the dimension of exceptional sets for orthogonal projections has shown us that even in the abstract world of math, there's always something new to discover, and those discoveries can have ripple effects we might not even imagine.